Hello, hello, hello. This is Nicholas, and I wanted to talk a little bit about the dot product because I think the dot product is, for the most part, just kind of memorized. And so I want to give some motivation behind the dot product. So let's assume we're in two dimensions, R2, for the sake of simplicity, I guess. And let's imagine that we've got this vector and this vector right here, okay? And let's draw this line here, and this angle theta is the angle between the two vectors. So I've just picked any two vectors here. So this is called vector A, and let's call it vector B. Okay, and then maybe this is at the origins of whatever coordinate system we're using. So now you probably, actually, I want to, let me call this A instead. You'll see why in a second, and let me call this B. Okay, so you have probably heard the definition that vector A dot vector B is a scalar. It's the magnitude of vector A, a scalar, times the magnitude of vector B, also a scalar, times the cosine of the angle between the two, which is, again, a scalar. And so what does that definition actually tell us? Well, we start with, let's look at the B cosine theta part. Magnitude of vector B times the cosine of theta. If this part B cosine theta, it would be this part here going along the direction of A. So the B cosine theta tells us how much of B is going in the direction of A. And so we multiply that by the magnitude of A. If we were assuming that A and B are unit vectors, so this is 1, this is also 1, and then maybe we could picture them in maybe they're in some sort of circle or something like that, and then they're both of those vectors are you could think of them as radii to the circle if you want, but that's not really necessary. But the idea is that this would then be A hat, because we just put a hat over them if they're unit vectors, and B hat. And still, if we were to draw this line, this would be the B cosine theta part, the red vector. And so if we're assuming them to be unit vectors, then the magnitude of vector A hat is just 1 by definition. And so what the dot product really tells us, since we can scale any vector by a scalar, that's why they're called scalars, is because they scale vectors. We can scale any vector to a unit vector. So we can scale any two vectors to a unit vector. And when we do that, what the dot product is really all about is telling us how much of one vector lies in the direction of another. So we would just have, in this case, that vector A hat dot vector B hat is just the cosine of theta. And this is why I have drawn the unit circle, if you will, because if you think of it in a unit circle, then the dot product is, that's all the dot product is doing, is telling us what component of, or how much of, it quantifies how much of one vector lies in the direction of the other. And so in this case, that quantity, the quantity of vector B hat that lies in the direction of vector A hat, is literally just this angle, the cosine of that angle. Now, you also have probably heard of the piecewise product definition of the dot product, and that is, for example, if I had vector 1, 2 dotted with vector 3, 4, then my new vector would be 1 times 2, or 1 times 3, or 3, plus, or oh my gosh, I'm thinking of cross product. Let me start that over. Okay, if I have 1, 2, and I dot that with vector 3, 4, then my dot product, which is a scalar, you get 3, 1 times 3, plus 2 times 4, or 8, and so the dot product is 11. in this particular case. And so that definition doesn't seem intuitively the same as this geometric definition. And let me just show you that it is. If I have any old vector A, I can always break it down into its components. So let's call this a sub x times I hat. So a sub x being the component of A in the x direction, plus a sub y j hat. And likewise for vector B, we'll call it b sub x I hat plus b sub y j hat. And so if I were to literally take their product, if I were to literally take the product of A and B using standard distributivity rules, then I have a sub x I hat plus a sub y j hat and b sub x I hat plus b sub y j hat. And so if I literally take their product together, I'm imagining these just as products because that's what I'm doing. I get a sub x b sub x times I hat dot I hat plus a sub x b sub y times I hat dot j hat plus a sub y b sub x times j hat dot I hat, and I could have wrote that as I hat dot j hat, doesn't matter, plus a sub y b sub y times j hat dot j hat. And now notice what I said before about the dot product being all about how much of one vector lies in the direction of the other, that scalar amount. Notice then it would make sense that if I and j are defined as the two basis vectors in two-dimensional space, which would imply that they are perpendicular to one another. In other words, this would be I hat and then this would be j hat. They're perpendicular to one another. And so therefore, the component of whichever vector you choose lying on whichever other vector would be 0. No component of one vector lies on any component of any other because they're perpendicular, they're orthogonal, or normal, however you want to say it. So in other words, that dot product then would be 0. And likewise here, it would be 0. And so if we have I hat dot I hat, or any vector dotted with itself, well, not any, if we have any unit vector dotted with itself, then we're going to get that same vector back. Because if I look at I hat and I dot I hat with itself, that's just asking how much of that blue vector lies on top of that black on top of that black vector that I've originally drawn. Well, all of it. They coincide with each other. They're the same exact vector. So their dot product would be the same exact vector. And so in other words, what I'm saying is that I hat dot I hat is 1, and j hat and j hat dot j hat is also 1. So what I'm claiming is that a sub x b sub x plus a sub y b sub y is another way to write this dot product as a consequence of this geometric definition. And that is where the piecewise multiplication of the dot product comes from. And let me actually take a look at this specific example. Oh, and by the way, I just used 2 dimensions for simplicity's sake, but what I've done here is certainly not limited to 2 dimensions at all. Foiling is an n-dimensional thing. Breaking a vector up into its components by perpendicular dimensions is not limited to 2 dimensions. That can be done in any arbitrary number of dimensions. So if let's consider the vectors 1, 2, and 3, 4. If I imagine them as position vectors in whatever coordinate system I'm using, 1, 2, that's going to look something like that. And 3, 4, so I go to the right 3, and I go up 4. Let's call this 1. Oh, gosh. Can I even draw the vectors right? Okay. That's 1, 2. And then we go 3, 4. So we're going to be right here, like that. And so if I were to zoom in, I guess this is a little hard to draw, but the angle in between these two vectors, that small angle there, would be theta. And I guess since it's a small angle, it's also the sine of theta. No, I'm just kidding. That was a physics joke. Anyway, so what that tells us is that, okay, well, first of all, the magnitude, let's call this first vector, vector v, and let's call the second vector, vector w. Then the magnitude of vector b is just you square each term, add them up, and then take the square root. So the square root of 1 plus 2 squared, or 4, and so the magnitude is root 5. So this length here is the square root of 5. And then likewise, the magnitude of vector w is the square root of 3 squared, which is 9, plus 4 squared, which is 16, or just 5. That's interesting that, okay. So the magnitude of the 3, 4 vector is just the square of the magnitude of the 1, 2 vector. So what this tells me is that if I were to, what does the 11 mean, right? What does the 11 mean? Well, if I were to scale these down and make them unit vectors, so in other words, just divide by their magnitudes, then the new vectors v hat and w hat that I would get, v hat would be the vector 1 over square root 5 and 2 over square root 5. And w hat would be 3/5, comma 4/5. So if I were to look at those, now I'm just going to guess here, but let's see. What I'm trying to get at is that the 11 means that if I were to take these as unit vectors and then compute the dot product using the piecewise multiplication method, that would probably be the easiest. Then, well, let me do that. Okay, 1 over 5 square root 5. Or 3 over 5 square root 5 plus 8 over 5 square root 5, which is 11 over 5 square root 5. So that's not a coincidence at all, right? I just divided by 5 square root 5 because I divided by each of the original magnitudes. And so 5 square root 5 is approximately, well, let's see, the square root of 5, that's a little bit greater than 2. And then that's about 2.23. And if I multiply that by 5, I get 11.18. So if I take 11 and divide it by 11.18, I'm going to get 0.98, call it 4, 0.984. So if I were to scale these down as unit vectors, what this means is that if this, I'm just going to draw them very roughly. Let's say that's v and that's w. This is w and this is v. So what that's telling me is that approximately 98.4% of vector v also lies in the direction of vector w. So that's a concrete meaning of what the dot product actually gives. It's not just some random number that we're pulling out of thin air here. And one other thing I would like to mention is that the dot product is also tied into the law of cosines. So if I were to imagine a triangle, so let's see. If I were to imagine a triangle here and think of the side lengths as vectors instead. So let's call this our triangle. So this is vector A, this is vector B, and what they're going to do is they're going to add to create this new vector C. And so, let me zoom in. And let's call this angle here theta. So, what the law of cosines tells me is that the magnitude of vector C squared is equal to the magnitude of vector A squared plus the magnitude of vector B squared minus 2 times magnitude of vector A times magnitude of vector B times the cosine of the angle between vector A and vector B. And you should see that this whole side here is all scalars, and so likewise C, magnitude of it, will also be a scalar. So what can I say? I can say that the magnitude of vector C squared is just the same thing as C dot C. Why? Because if I take any vector and I dot it with itself, how much of that vector lies in the direction of that same vector? Well, all of it, right? So in essence, you're just taking the length of that vector and just multiplying it by itself. And so the magnitude of that vector squared is, in general, that vector dotted with itself. But C, I said before that C would be the subtraction of A and B. In other words, vector C is going to be vector A minus vector B dot vector A minus vector B. And if you can't see why it's subtraction, well, look at it this way. B is pointing in this direction here, so negative B would be pointing in that direction there, an equal and an opposite direction. And so the arrow then would be pointing, see, our vector C is indeed going that way. It's starting here and it's going over there. So we have to be subtracting B, not adding B. And also, of course, we're going up a distance A, so we're adding A and not subtracting A. So C is indeed vector A minus vector B. And now if we're to actually do this dot product, then what we get is using literally the distributive product. I mean, we're taking an actual product here. We have vector A dot vector A minus vector A dot vector B minus vector B dot vector A plus vector B dot vector B. And so then the magnitude of vector C squared is, if I take any vector and I dot it with itself, I get the magnitude of that vector squared. And so likewise here. And now this is the same thing, so I can make it minus 2 times vector A dot vector B. And of course, that's still the same thing as vector A, the magnitude of vector A squared plus the magnitude of vector B squared minus, and now if I use the original geometric definition of the dot product, that's minus 2